Bismillahirrahmanirrahim. Assalamu alaikum. Hi everyone, how are you? Today we are going to be solving some problems in chapter 1 after we have finished that last time. So this is what we are going to do. So just to look at it in a moment, we will open the problems. So these are the problems that we are trying to solve here, and we are going to start with problem number 1. So I think we're ready with it. So problem number 1 says, an employee works in a plant with a FAR of 4. If this employee works a 4-hour shift, 200 days per year, what is the expected deaths per person per year? So we want to calculate the expected death per person per year by knowing the information of the FAR and the amount of hours that they're working on. So if I would say chapter number 1, so this is chapter number 1, and in this chapter we will try to solve the problem. So where's my toolbar? Okay, okay, that's great. So my toolbar, I have it here. So the FAR is equal to 4, as it was stated in the problem, and of course we calculate this based on the 10 to the power of 8 exposed hours. This is the definition of FAR, right? So talking about the equation, if you just can remember the equation was FAR is equal to the number of fatalities multiplied by 10 to the power 8, and that was the number of hours, divided by the total hours worked, and you just can continue that worked. Okay, so what do I want to find? I want to find the number of deaths, which is the number of fatalities. So this is the thing that I'm trying to find. So simply I'm going to multiply FAR with the total number of hours. So that will be the deaths that I'm trying to calculate per person per year will be equal to 4 hours per shift, that's the total hours worked, into 200 shifts per year, and this is multiplied by the FAR, which is 4 deaths per 10 to the power 8 hours, and by that I'm going to get the answer, which is 3.2 into 10 to the power minus 5 death per person, of course, as we said, per person per year. So that is the solution for the first problem. I think that was straightforward and easy. So let's go now to problem number 2. So that is 1.1.2. So going to problem 1.2, the problem says that there are three process units are in a plant. The units have FARs of 0.5, 0.3, and 1 respectively. So 0.5 for the first one, the 0.3 for the second unit, 1 for the third unit. The overall FAR for the plant, assuming worker exposure to all three. So the worker is working, or he's exposed to all three units. So because he's exposed to all three units, that means we need to add all the FAR for that person. However, the second part says that if you assume that the units are far enough apart, so each unit is just far away from each other, that an accident in one would not affect the workers in another place. So he's not really exposed to the three, he's exposed to one only at a moment, and it will never be that he's exposed to the three. So if a worker spends 20% of his time in the first one, the process area 1, and 40% in the second area, and 40% in the process area number 3, what is his overall FAR? Here the overall FAR will be the weight average. It will be 20% multiplied by 0.5 plus 40% to 0.3 plus 40% to 1, and you will get the answer. I think so that is straightforward to solve the problem. So I'll just write that. So we have three process units of FARs of 0.5 and 0.3 and 1.0, and going assuming, as they have stated, exposure to all three units, the net FAR, net FAR, is going to be 0.5 plus 0.3 plus 1.0, which is equal to 1.8. Going to part B. Part B, since we have 20% of time in area 1, and that was with the FAR of 0.5, and the second one we had 40% of time in area 2 with FAR of 0.3, and the third one was 40% as well of time in area 3 with FAR of 1.0. So the answer will be simply the net FAR is equal to 0.2 into 0.5 plus 0.4 into 0.3 plus 0.4 multiplied by 1, and by that I'm going to get the solution, which is equal to 0.62. And you can see like in both cases the net FAR is still greater. The first one, it was greater, definitely is exposed to all of them, but the second one, it will be a weight average between the three mentioned process units. So that is for 1.2. That is the answer for 1.2. Okay, so now to go to 1.3. So let's see the question of 1.3. Assuming that the car travels at an average speed of 50 miles per hour. So it travels at a 50 miles per hour. How many miles must be driven before a fatality is expected? Beautiful. That's a nice question. So we have the 50 miles per hour that we have here, and actually from one of the tables, which is table 1.4, I think it's table 1.4, you can have a look, and the FAR traveling by car is already given in that table to be 57 deaths per 10 to the power 8 exposed hour, and by that we can calculate the expected fatality, or how many miles must be driven to for a fatality to happen. So let's go and solve the problem. So what do we have for problem 1.3? We have that from table 1.4, we already know that the FAR traveling by car, is equal to 57, I'm going to write it here, 57 deaths per 10 to the power of 8 exposed hours. This is 10 to the power 8 exposed hours. So if I would say that, so for one death per year, how much it will be? For one death, it will be 10 to the power 8 is equal to divided by 0.57. We will have the answer will be 1.75 into 10 to the power 6 hours, which means that I will need 1.75 into 10 to the power 6 hours to have one death only. Okay, because here we are talking about 57 and 10 to the power 8, but for one death we need to divide by 57. I don't know if you can remember that we say that 57 in 10 to the power 8 hours. How many hours? Sorry, I'll rewrite that. So how many X hours I would expect to have one death? Okay, so what do? We just multiply 1 into 10 to the power 8 divided by 57 to find X, and this is what I have done. And since now we have the answer of the number of hours, which is time, so I do have time, and I'm already given the velocity, and they are asking about the distance, and we already know the relationship between these three. So all what we need to do is the distance is equal to the multiplication of velocity into time, and this will be 50 miles per hour. 50 miles per hour into 1.75 into 10 to the power 6 hours, and this will cancel that, and we will have the answer to be 87.5 million miles. So that is inshallah more than enough for you to drive, and don't worry about dying. Okay, so that is the answer for the third problem 1-3. That's the answer for the third problem 1-3. Great. So let's go and solve 1-4. So let's go and solve 1-4. Okay. And by the way, we will not solve all the problems, but we'll try to solve whatever we can to make it even simpler for you, and to understand how to use those equations and how to solve them in the exam. Okay, so a worker is told her chances of being killed by a particular process are 1 in every 500 years. Oh, okay. I was not expecting that kind of a question, but that's fine. So a worker is told her chance of being killed by a particular process is 1 in every 500 years. Should the worker be satisfied or alarmed? What is the FAR? Assuming normal working hours, so that is the normal hours, talking about how many hours per year, which is about 2,000 hours per year. And the 2,000 hours per year is calculated by saying that I have 8 hours per day into 5 days per week. So that is 40 multiplied by 50 weeks per year. Without the holidays, that will be 40 multiplied by 52,000. So this is where it comes from. Okay, so let's go back. And the death what is the FAR and the death per person per year? What should be her chances be, assuming an average chemical plant? Okay, great. So let's solve the problem. So just to recall what we should do exactly, first we want to find the death per year. Death per year, and this is obtained from as we have solved earlier. So not the number, well, the working hours. Let me say that the working hours, which is 2,000, multiplied by the number of death per year. The number of death per year, which is the FAR. I mean, we want to find the FAR. Let me remember the question. So they were asking about the FAR and the death per person per year. So the death per person, here we want to define the death per person per year. So the number of working hours into the FAR, which is the number of death per hours. Okay, so we need to find what? We need to find that so that we can solve our problem. How can we find the FAR? The FAR, sorry for that. Okay, the FAR, we need to know how to calculate it. First of all, if we just know the number of working hours, the number of working hours is equal to the 8 hours per day, the 8 hours per day into 5 days per week into 50 weeks. This will be equal to 2,000 hours. Okay, so this will be equal to 2,000 hours. Okay, and if I say that now, if I have 2,000 hours per year, and they are telling me that for 500 years, if you just can recall, the question is that it said that the possibility here is 1 in every 500 years. 1 in every 500 years. Okay, so we know that it's 1 death for every 500 years. So if we multiply into 500 years, the answer will be it will be 10 to the power 6 hours. So 10 to the power 6 hours is for what? Is for one death. Okay, 10 to the power 6 is one death. And actually, if you think of FAR is based on 10 to the power 8 hours. So if you calculate x here, x would be 10 to the power 8 multiplied by 1 divided by 10 to the power 6. So x, which is the FAR here, the FAR will be 100. So we know now the FAR is equal to 100, and if the FAR is equal to 100, should she be alarmed or not? You just think of it. Yani the worker must be alarmed. The worker should be alarmed. It sounds that it was like every 500 riyals, but it should be alarmed. Why it should be alarmed? Because for an average plant, if you go to table 1.4, again table 1.4, you can see that the FAR is equal to 4 deaths per 10 to the power 8 hours. I'm having here 100, not 4. And imagine how much is that. So that is really a very big number. And if you just count it, I don't know how much is that. It's like 100 divided by 4. Oh my God. That is like 25 times. Oh my God, that's 25 times. That is really a big number that we need to talk about. So again, this is what we have. But actually, if you want to calculate it per year, if you want to calculate it per year, because here we are talking generally for 10 to the power 8 hours without mentioning, well, it is mentioned per year, but we would say that if you want to calculate how many deaths per year, and then how many years per death, we can calculate the number of chances for that year of exposure. Okay, so it could be that she doesn't need to be alarmed, because there's some kind of an information that we need to calculate here. And what do I mean is that when you go to the death per year, number of deaths per year, which is 2000 hours, multiplied by 4 deaths over 10 to the power 8 hours. So now calculating per year, it will be 8 into 10 to the power minus 5. Okay, I just want to highlight that there are many people working, right? So it's 8 into 10 power 5. So how, if our calculates now years per death, I just take it upside down, which is 1 into 8 to the 10th power minus 5. This would be like 12,500. That means the chances should be 1 in 12,500 years of exposure. So what I'm trying to say here, well, it sounds like now that it is not alarming, because just based on what we have mentioned, it looked that it was alarming, but don't worry, she will live. She will live. Great. So that is 1.4. That is 1.4. And we can go on solving 1.5 and 1.6. I'm not sure that you're ready to solve that by yourself and to have it a go. And because if you have it a go, you'll be more comfortable, and then you can come back to my video for 1.5. Okay, so just stop it, solve 1.5, and hours after solving 1.5, please do come back. I hope just now you went back and you went and tried to solve the problem. So you read the problem and it said a plant employs 1,500 full-time workers in a process with a FAR of 5. So 1,500 people working. How many industrial-related deaths are expected each year? Okay, we want to see how many people are expected to die each year. So the total working hours, because I'm having many people there, so the total working hours per year is going to be equal to 1,500 workers multiplied by, you remember, 2,000 hours. Okay, so 2,000 hours per one worker. That will be 3 to 10 to the power 6 hours. So I have the number of hours. So what I need to calculate now? I need to calculate the death per year based on the FAR that I already have. What was the FAR? It is 5. Okay, the FAR is 5. So we know that FAR is equal to 5. So what I need to calculate is the deaths. Okay, it is the death per year. The death per year is equal to 3 into 10 to the power 6 hours, and that is multiplied by 5 deaths per 10 to the power 8 hours, and this is the FAR. Okay, this is the FAR, and this is equal to 0.15 death. Okay, wow, 0.5 death, and 0.15 death. It means that we are expecting to have one death. One death can be expected. Every 6.6 years. Why? Because here I'm calculating the deaths per year. So this is per year. Okay, so here we are talking about how many deaths we are going to have per year. So if you just multiply it, if you want to make this one death, so it's like that again. It's the same story that I showed you before. So it's like 0.15 in 1 year. So this is 0.15 death in 1 year. So what I want to know how much death, one death, x. So x is going to be 1 divided by 1.15. It will be 6.6 years. So that's the answer. You already have it here. So this is the answer for 1.5. This is the answer of 1.5. Beautiful. Beautiful. Okay, so again, if you just get a chance to solve 1.6, just get a chance to solve 1.6, and then you can come back. So consider example. I'll just keep quiet for a moment. So that is 1.6. Okay, go and come back. Okay, I hope you're back now after you try to solve it. So considering the same example of 1.4, how many hours must be traveled by a car for each hour of rock climbing? Okay, we are talking about not the FAR of rock climbing. Rather than 1.4, we were talking about, okay, that was chance being killed by a different story. Okay, so let's go back. So how many hours must be traveled by a car? Oh, sorry, which question am I? Yes, 1.6. How many hours must be traveled by a car for each hour of rock climbing to make the risk of fatality by car equal to the risk of fatality by rock climbing? Of course, rock climbing is much higher, if you can remember. So simply in 1.6, they want to compare car with rock climbing. How much hours you need to travel by car to have some similar effect. So if I talk about FAR of rock climbing, in which you do this thing rarely, and that's the idea of the question. You do this thing rarely, so it is 4,000. Okay, and the FAR of traveling. The FA of traveling a car by car is equal to 57, and actually this is 57, but you travel a lot by car, right? So it is different. So if you just divide 4,000 divided by 57, you will get 70.2 hours travel by car. And if you think of it, like how much do you travel? You travel like 1 hour per day, so that is like 70 days. So within 70 days, it is equal to our rock climbing that you do every year once or twice, right? So that 70 days is about from 360 days. It's about 1/5. Okay, so it's 20%. So what I'm trying to say here is that Now it looks like the rock climbing, what you're going to do is safer in a sense, because you're going to travel much more and you're going to have the possibilities of getting a fatality by car much more than rock climbing. I hope this gives you an idea about what we are trying to say here. Great. So that is 1.6. That is 1.6. Now we have taken from 1.1 to 1.6. It was all about the FAR. However, now we are going to be shifting to a different kind of solutions. Now we are going to talk about the 1.7, solving 1.7, where we are going to go to the initiation, propagation and termination steps. So let's go ahead and solve it. Let's go ahead and solve this problem. So 1.7, what does the question 1.7 say? Identify the initiation, propagation and termination steps for the following accident reports. Suggest ways to prevent and contain the accidents. Okay, so let's look at A. We can solve A and B. Let's see how fast I can go with that. A contractor accidentally cut into a 10-inch propane line operating at 800 psi at a natural gas liquids terminal. So the initiation of this accident was what? Was cutting a 10-inch propane line. Very clear. What propagated after that? The large vapor cloud, estimated to cover an area of 444 acres, was ignited about 4 to 5 minutes later by an unknown source. Definitely this was the propagation. Was the leakage of the propane was the only thing? No, actually not. The liquid products from 5 of 26 salt dome caverns fed the fire with an estimated 18,000 to 30,000 gallons of LPGs for almost 6 hours before being blocked in and the fire extinguished. So there was a leakage. Number two, there was a vapor cloud that could have caused some explosion. And actually, what did it cause? It caused, my God, the destruction of the fire pump equipment. So both engine fire pumps failed. You can see that. One because intense radiated heat damaged its ignition wires, and the other because the explosion broke a slide. Oh my God! Explosion broke a slide gas fuel gauge, spilling diesel fuel, which igniting, destroying the fire pump engine. Everything went bad. Oh my God! So what was the termination? The termination was the propane is finished. Okay, so there was nothing that we can do about here. So if you look at it, so if you want to apply the initiation, how this was initiating by cutting into 10-inch propane line. So that was why this accident initiated. What about propagation? Well, it propagated in several forms, where there was a leakage of propane, and then there was a formation of vapor cloud, and then this vapor cloud ignited. So there was an ignition of that vapor cloud, and because of that a lot of destruction happened. And one of the things that happened, that the destruction of the fire pump equipment. And if you're going to go to the propagation, the termination part, you go to the termination part. It terminated because of blocking in of the propane. So the propane itself, now it's finished, or there was a blockage for this propane going out and leaked, so it just stops there. Great. So that was the solution of 1.7 for part A, and I think so it's a good chance for you to read part B. And I'm just leaving things for you because it helps, by the way. It helps a lot for you to go through the solution by yourself. Okay, so let's go to the next step. So we do have the problem 1.8. 1.8. The airline industry claims commercial airline transport has fewer deaths per mile than any other means of transportation. Really? So they're claiming that they're better than the others. Okay. Do the accident statistics support this claim? Well, let us see. In 1984, the airline industry posted 4 deaths per 10 million passenger miles. Beautiful. Is this good or not? We're not sure yet. What additional information is required to compute a FAR, a fatality rate? Fatality rate. Okay, so let's calculate this. Let's calculate this and see how it goes. So 1.8. So we are talking about an airline industry. Okay, so we are talking about an airline industry where they are claiming that they have fewer deaths. If you go to the table 1.4 again, you're going to see that the FAR, FAR for cars, let me see, say for cars it was 57, and for bicycle it was 96, and for air it was 240. Great. So based on the per hour basis, if you're going to take that on a per hour basis, traveling by plane is almost, if you can see, that's about 5 times, it's about 5 times more dangerous. Well, and again, if you are taking a per hour basis, but of course the number of hours that you travel by car is not equal to the number of hours you travel by air. You travel once per year or twice per year. Car you drive every day. Okay, so we need not to confuse things together. But as we can see here, that if you see that this is 240 and this is 557, so if you divide 240 divided by 57, that is approximately 5. So this is just the idea about it. Okay. However, it doesn't mean that it is safer or not. Okay. So if you just want to compute the FAR, if you just go back to the question, not to forget what you are trying to target here. So they claim that the industry posts for a death per 10,000 passenger miles. So we need to calculate and see that if this is okay, we are happy with the statistics, which shows it is good or not. So to compute the FARs, or let me say that we want to calculate or compute. So we want to, let me write that again. So we want to compute the FAR, FAR. Okay, so what do we need to compute it? We need the total hours exposed, right? Because we cannot calculate it without knowing the total hours exposed. So to know the total hours exposed, well, if we have time and velocity, right? Sorry, that's time. If we have a velocity and we already have the number of miles, which is the distance, we can calculate from this to the time, right? So we can calculate the time, which is total number of hours, so that we can go to our next step. So we need to suppose here an information. For example, for air, it's about 200 miles per hour, the velocity, and if we know that this is 200 miles per hour, and we already also know that it is based on 10 to the power, the 10,000 million miles. So we have everything here. So the total hours exposed is equal to 10 into 10 to the power 6. Let me write miles. That will be better. divided by 200 miles per hour, and of course this will cancel out with that, and that will be equal to 50,000 hours. Okay, so here we have calculated the amount, the total numbers of hours, and now we can calculate based on that the FAR. Well, the FAR is equal to, this is given for death, 4 into 10 to the power 8, and then again I'm going to show you that in 1.8 it said that in 1984 the industry posted 4 deaths per 10,000 million passenger miles. So in 1984, so that is the deaths per year. So that is 4 into 10 to the power 8 hours. Okay, 10 into 10 to the power 8 hours. This is 10 to the power 8, the one that we always multiply. We need to multiply by 10 to the power 8 based on 10 to the power 8 hours, divided by the number of exposed or working hours, and this number of working hours, and this is equal to 8,000. Oh my god, the FAR is 8,000. I never seen this before. Oh my god, this is like, oh my god, what was the FAR for airlines? If you just can recall, what was the FAR of airlines? It was 240. Oh yes, it's 240. My god, did you see that? Did you see that? It's 240. Okay, so you're talking about 240. Oh my god. So here you're talking about something like 8,000. Let me do that in blue. So you're talking about 8,000 divided by 240. That's about, how much is larger than this? I can't calculate it. It's 10, 30, 10, and then 40 times, and that's less than 40 times, but let's say about 35. I don't know, but that is really crazy. That is really very high. They're really very high. Okay, so that was the FAR. That was the FAR, and we can see that what they have reported was very tricky. Okay, so what additional information is required to compute the FAR and the fatality rate? Okay, the fatality rate, I don't know if you can recall what is the equation, because we did not take that before, so I'm going to write the equation. So, the fatality rate is equal to, number of fatalities per year. So how many people die per year, number of fatalities per year. And if you remember that we already have this as 4, divided by the total number of people in applicable population. So that this is divided by the total number of people in applicable population. Total number of people in applicable population. Okay, so how many people? I don't know. So I would say that I have this information here. I have this information, but what about that? How could I calculate the total number of people? Well, I already know the number of miles. Well, I already know the number of miles. So if I say that the number of miles that they were mentioning there was 10 into 10 to the power 6 miles, which I would say that is equal to 10 to the power 7 miles. So how many miles are usually traveled by people, right? So people travel on average. We are assuming some numbers here. Travel on average something like 300 miles. We would say 300 miles. Okay, so that is like 500 kilometers or something like that. So we're talking about 300 miles. So based on the per person, people travel on average 300 miles. So this is 300 miles per person. Okay, 300 miles per person. So if you divide now, just to calculate how many passengers, total persons that I would have based on the 10,000 miles covered. Okay, divided by 300 miles per person, and this will be equal to like 33,333 persons. And based on that, now I'm going to go and substitute this value here. So substitute this value here. So and when I do substitute it here, the answer will be equal to 4 divided by 33,300, which is equal to something like 1.2 into 10 to the power minus 4, which is also high, very high. Oh my god, that's really high. Okay, so the fatality rate is high, really high. You're talking about 1 into 10 to the power minus 4 is the fatality rate. If you just compare that with the numbers in the tables, you can see that is really high. Okay, so this is the way of how we have calculated to solve the problem number 1.8. Beautiful. So we have calculated, we used, and now we solve for the FAR, we solve for the fatality rate, and we need to solve an example on how to calculate the OSHA incident rate. We also covered now the initiation, propagation, and termination steps as well. So let's solve 1.9. Yep. So let's solve 1.9. In solving 1.9, let's read it. A university has 1,200 full-time employees. That is less than University of Bahrain. University of Bahrain is I would say it's about 2,000 employees. Okay, so let's go back to this university. 1,200 full-time employees. In a particular year, the university had 38 reportable lost time injuries. Okay, so people have been injured, and because of that, we have 38 lost time injuries, with a resulting of 274 lost work days. So these are the number of work days that we lost because of those injuries. So one person takes 1 day holiday, another person takes 1 week holiday, a third person takes 1 month holiday, I don't know. Okay, so compute the OSHA incident rate based on injuries and lost work days. Okay, that is a bit challenging. That's a bit challenging. So if you just go through the definition, so what was the OSHA? Let me write that in blue just to tell you that it is like an equation. So the OSHA, the OSHA incident rate. Okay, the OSHA incident rate is equal to number of lost work days multiplied by 200,000 hours, okay, divided by total number of hours, or let me say, just simplify it, total hours worked. Okay, it is the total hours worked by all employees. And of course here it says incident. So if you just want to put another thing here rather than writing incident injury, so you will say here the number of injuries. Okay, so it just goes like that together. So if I want to calculate the total hours worked, I need to multiply. If I want to calculate the number of lost work days, I need to multiply these two, which is the OSHA incident rate with the total hours worked. And of course, you know the math. I don't need to talk about it a lot. But let me calculate. Now I need to have these things, right? So I have the thing which is at the top. I need to calculate total hours worked. So what is the total hours that had been worked? Okay, so the total hours worked is equal to, I have 1,200 employees. And each one is working 2,000 hours per employee, of course, and that will be 2,000 hours per year if I would be more specific. And this will be like equal to 2.4 into 10 to the power 6 hours. Okay, so what about now? If I calculate this, now I can calculate my OSHA incident rate. So OSHA injury rate. because here he's talking about the injuries as an incident. So that if this is equal to 38 injuries, 38 injuries, what did I get this 38? So if you just go back, an university has 1,200 full-time employees. In a particular year, this university had 38 reportable lost time injuries. Okay, so it had a report of the 38 injuries, and this is divided by 2.4 into 10 to the power 6 hours. And in our equation, we multiplied by 200,000 hours. So this is multiplied by 200,000 hours, and this is equal to 3.17. So the incident rate is 3.17. and very similarly, so this is part A. Very similarly, if I want to calculate the work days, if I want to calculate the lost work days, so that is the lost work days, this is equal to the 274 lost work days mentioned in our problem. Again, if you go back, it's written 274 lost work days, and this is the 274 lost work days, and we divide that by 2.4 into 10 to the power 6 hours, the one that we have found. And of course we multiply this by 200,000, we multiply by 200,000 hours, and we get our solution to be 22.8, and this is the way how we are finding our lost work days. Great. So that was 1.9. That was 1.9, the answer of this problem. Okay, so I think so we can take a break now, and we can continue with more problems if we do require more to solve more problems. But for today, I think so that is good enough. So we will be seeing you in the completion of solving more problems, and we can see that we have more problems here. We are going to select from them because there are a lot. So we're going to select from these equations, from these problems, what we can to solve. So we've solved the first 10 problems in chapter number 1. I hope that was useful for you, and good luck in your work, and wish you all the best.